as we're talking about modeling real-world situations with linear functions, we have to be aware of one limitation, and that is real-world data isn't always or usually perfect. Real-world data is not perfect. Here's what I mean by that. Let's say I collected some data from some people. I want to know how many sodas they drink in a week and how many bottles of water they drink in a week. And so I compare the number of soda versus the number of waters. So I am going to collect my information in a table. We've got sodas and we've got waters. Well, one person drinks 8 sodas and 3 waters. The next person drinks 4 sodas and 6 waters. The next person drinks 9 sodas and 1 water. The next person 3 sodas and 5 waters. The next person 6 sodas and 2 waters. The next person 2 sodas and 6 waters. Well, to help visualize what these numbers are doing, because they're kind of random right now, we can build what's called a scatter plot, where we're going to graph each of these points. So for the sodas, we're going to make those our x-axis or horizontal distance, and the waters, we're going to make that the y-axis or vertical distance. So I'll go over, my first person is 8, 3. 8, 3, I go over 8, up 3, and I'll put a dot to represent that first person. Next person's 4, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Over 4, up 6 is about there. The next person is 9, 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1. The next person is 3, 5. The next person is 6, 2. And the next person is 2, 6. And what I see is these dots don't actually make a straight line. They're kind of all over the place. But what I can see is the scatter plot. The dots do kind of follow a trend. And when I can see that trend, we can draw the line of best fit. And the idea of the line of best fit is it is going to follow the data as close as possible. So for example, on this one, I can see the data is kind of going downhill, and if I were to draw a line right through the center of the dots, we could say that line follows the data pretty darn close, and we can kind of eyeball where we think that line of best fit should go. You might argue maybe it needs to be a little steeper, maybe a little shallower, or maybe move over a little bit, but that's kind of the general direction of the data. And so now I can kind of get a feel for what the data is doing. It's going downhill, and it's kind of following this line closely. Now, we want to kind of quantify our way to make that line of best fit. And that's what we're going to look at next. And what we're going to do is we're actually going to use technology to find the best fit line. And the math equation behind this is probably more complex than we need to go into in the scope of this course. But what I do want to show you is we can use some technology and interpret the results of this analysis. Let's say I want to know if there's a relationship between the temperature outside and the number of chirps we hear from a cricket. Chirps versus temperature. So let's have some data. We're going to have some chirps, and we're going to have temp. We're going to have several data values here. When there were 44 chirps, I looked outside and the temperature was 80.5 degrees. When there were 35 chirps a minute, I looked outside and saw the temperature was 70.5 degrees. When there were 20, we'll say 20.4 chirps, they didn't quite finish this last chirp, there were 57 degree temperatures. Let's say a 33 chirps happened when it was 66 degrees. 31 chirps happened when it was 68 degrees. 35 chirps happened when it was 72 degrees. And about 18 and a half chirps when it was 52 degrees. 37 chirps when it was 73.5 degrees. And finally 26 chirps when it was 53 degrees. And we want to make a scatter plot of this data and a line of best fit, but we want it to actually be the line of best fit. And so we're going to use a program called Microsoft Excel to help us do just that. Here in Excel, I have copied the exact same data that we just had. So you can see in column A, I've got chirps. In column B, I have temperature. In order to make a scatter plot with this information on it, we are going to highlight both columns with our data. Then I'll go to Insert. And under Charts, there should be an option that looks like a scatter plot. Go ahead and select that first section, and that's going to make a scatter plot of how the temps are related to the chirps. What's nice about this scatter plot is all I have to do to get the line of best fit is I hit the little plus sign next to the chart and then select trend line, and it's going to make what's actually the line of best fit. Now, we still might wonder, what is the equation of that line of best fit? To get the equation of that line of best fit, all I have to do is double click the line, and a Format Trend Line option will show up on the right here. And I can scroll all the way to the bottom and tell it to display the equation on the chart. When I click that box, I see this equation comes up, y equals 1.1432x plus 30.281. That is my line of best fit equation. So we went onto Excel and we learned how to do this, and we came up with our line of best fit equation is y equals 1.1432x plus 30.281. That's going to be the best way to estimate the relationships between chirps, my x, and the temperatures, my y. Now I could use this equation that I've just found to predict future values. Let's say I want to predict the temperature when there are 39 chirps. Well, we said the chirps were the x values, so I'm going to plug that in for x in my equation, and we get y equals 1.1432 times our 39 chirps plus 30.281. And when I do that, I find out y is equal to 74.9 degrees. So it's almost 75 degrees if there are 39 chirps a minute. Now there's a little bit of a catch to this process, because when we're predicting using a line of best fit, that line of best fit didn't connect the dots perfectly, right? When we looked at our Excel chart, there was a little bit of a gap between the line and the dots sometimes along the way. What we might be curious then is, if there tends to be a gap, the question can be, how good is the estimate? Well, one way we can measure the quality of the estimate that we made is we find what is called the correlation coefficient. And we can do this on Excel again. The reason we're going to do this on Excel again is because the formula itself is beyond the scope of this course, but we can use Excel to find it and then interpret it in this course. So the way we're going to find the correlation coefficient in Excel is you can click on any empty cell and you're going to type equals and then CORREL, open a parentheses. Then we're going to select all the numbers in the first column, comma, select all the numbers in the second column. And when I hit enter or tab, it's going to give me the correlation coefficient is 0.9509. Let's go back to our notes. The correlation coefficient is R equals 0.9509. Now with the correlation coefficient, we always use the letter R. So if you're looking for the correlation coefficient, you're looking for the letter R on an output chart or just Corel on Excel. So what does this number mean? How do we interpret our correlation coefficient? How do we interpret R? Well, we do it in two different ways. First, we look to see if it is positive or negative. If it's positive, we will see that the graph and the line of best fit is increasing. Here's an example of what I mean by that. I might have some dots. But when I draw the line of best fit there, it's going to be positive going uphill and increasing. That means the R will be positive. In the negative case, if the dots did something like this, and I drew the line of best fit through them going down, that would make the R negative because it is decreasing. The next thing we look at as we interpret R is how close to the number 1 it is. If it is really close to 1.0 or negative 1.0, it's never going to be further away than 1. But positive 1.0 or negative 1.0, then the graph is a near perfect line. Or near perfect dots, I should say. So if the dots come like this, notice those dots can almost be connected with a perfect straight line. That's a near perfect 1.0 graph. Versus if it's close to 0.5 or negative 0.5, that is going to be a bit spread out. In other words, the line of best fit might go like this. That one's negative. But the dots are kind of far from it. They're still decreasing, but they're a lot more spread out. In fact, I guess we could even put a third one on here where it's close to 0. When it's close to 0, it really means there's no pattern. And it's hard to say if it's increasing or decreasing. Where do you draw the line? That's going to be no pattern, because the dots aren't close to any line. I guess the best you could do would be to draw a line right through the center, but even that's not informative because the dots are just all over the place. So as I look at the R that we got from our data with the chirps and the temperature, we see that the R value is 0.9509. That's a positive number, so I know things are increasing. As we get more chirps, we get more temperature. Things are increasing. Also, it's really close to 1, and so that tells me the dots are really close to the graph. Looking at the graph here, we see those dots really are pretty darn close to that line, so that matches my correlation coefficient of 0.95092. So real-world data is never perfect. What we have to do with real-world data is collect the data, find a line of best fit, and then we can use that line of best fit to make predictions.